Hello, everyone. My name is Dale Fredericks, and this is my Anatomy and Physiology presentation project. I will be talking about blood vessels and fetal circulation, and down below I have some learning objectives that we'll be talking about today. The first topic we'll be talking about is blood vessels. Blood vessels are like the body's highway, allowing blood to carry essential stuff like oxygen and nutrients to different parts. They are crucial for keeping our cells healthy and getting rid of waste. This presentation will break down how these vessels work and why they are so important for our overall being. The three main blood vessels compose of the tunica intima, tunica media, and tunica externa. The tunica intima is the innermost layer of the blood vessel wall. The tunica media, that is the middle layer containing smooth muscle cells, elastic fibers, and collagen. And then the tunica externa is the outermost layer. Artery classification. There's three type of arteries listed here. The first one is elastic arteries, muscular arteries, and arterioles. I have the structure, location, and the function listed below, and it describes like each one that they do. For instance, elastic arteries, they're characterized by a high proportion of elastin in the tunica media, providing elasticity. They're found closer to the heart, such as the aorta and pulmonary arteries, and they are able to stretch and recoil. The muscular arteries have a thick tunica media with smooth muscle cells. They distribute blood to various parts of the bodies. And the function, they regulate blood flow to specific organs by adjusting the diameter of the artery based on demand. Arterioles, they are smaller vessels with limited tunica externa and tunica media. They are found connected muscular arteries to capillaries, and they act as control valves, influencing blood into capillaries through changes in diameter. Some common features in veins and arteries. The tunica intima, they both arteries and veins have inner layer composed of endothelium, providing a smooth surface for blood flow. The tunica media both contain a middle layer, primarily consisting of smooth muscle cells, regulating vessel diameter and blood pressure. And the tunica externa, the outermost layer, provides structural support composed of connective tissue. Some key differences is the thickness of the tunica media. Arteries generally have a thicker tunica media compared to veins, and the presence of valves. Veins, especially in the extremities, contain valves to prevent backflow of blood. Arteries being closer to the heart do not require valves as the blood is under greater pressure. There are types of capillaries. There's continuous capillaries, fenestrated capillaries, and sinusoid capillaries. The continuous capillaries have a continuous and uninterrupted endothelial lining without pores, and I have a function for each one too. They are found in muscles, skin, and central nervous systems, forming a tight barrier that regulates the passages of small molecules and prevents larger substance from easily entering or leaving the bloodstream. Fenestrated capillaries have small pores or opening in the endothelial lining, coming in areas with high metabolic activity, such as the intestines, kidneys, and endocrine glands. Sinusoid capillaries have irregular gaps in their endothelial lining, making them more permeable. They are found in organs with significant blood filtration and exchange needs like the liver, blood, marrow, and spleen. The capillary bed structure is composed of the meta-arteriole, which is a short vessel connecting arterioles and capillaries, serving as a bridge between the two. Precapillary sphincters are muscular rings at the entrance of the capillaries controlling blood flow into them. And then you have the venules, small veins that connect blood from capillaries and start the journey back to the heart. I have a diagram here to show a visual representation of what these structures look like. Venous valves. Venous valves are like flap-like structures found in the veins, particularly in the larger veins at the extremities, like legs. The location of these are predominantly present in veins, especially those in the lower extremities where blood has to work against gravity to return to the heart. They prevent backflow, which is the primary role, and blood moves towards the heart. The valve opens, allowing it to pass through. However, when the blood tries to move in the wrong directions, the valves close, preventing backflow. Venous blood flow factors. There's muscular contractions, respiratory pumps, venous constriction. Muscular contraction, when you move, the squeezing actions of your muscles help push blood back to your heart, especially in activities like walking. Respiratory pump, when you breathe, the pressure changes in your chest, assisting in pulling blood back to the heart, making sure it keeps flowing smoothly. Venoconstriction. Think of it like veins getting a bit narrower, which boosts blood pressure and helps move the blood towards the heart, especially during stress or excitement. Roles of valves. Valves in your veins act like one-way doors, preventing blood from flowing backwards. This is crucial, especially in your legs, to make sure blood goes up towards your heart and not back down. Overall, these mechanisms work together to keep your blood flowing in the right direction, supporting your overall health. And here I have a list of essential terms. Understanding these terms is essential for discussing the complex world of blood vessels and their role in maintaining bodily functions. Next, we will talk. Oh, wait, there's a conclusion. Conclusion of blood vessels. Understanding blood vessel structures and function is crucial for grasping the complexities of the circulatory system. Key points include recognizing the three tunics, distinguishing artery types, comparing arteries and veins, comprehending capillary bed anatomy, and acknowledging the significance of venous valves. This knowledge is essential for appreciating how blood vessels contribute to overall health, ensuring proper nutrient delivery, waste removal, and maintaining the balance necessary for your optimal bodily function. Now we will be talking about fetal circulation. Fetal circulation is like special heart structures in a growing fetus, like the foramen ovuli and ductus anterius. Ensure the developing baby gets enough oxygen and nutrients while in the womb, even though its lungs aren't working yet. The blood vessels, like tiny roads, form a network to deliver these essentials and remove waste. This process sets the stage for a healthy start in life and impacts the baby's health even after birth. Fetal heart adaptations. A baby in the womb needs special heart structures because its lungs aren't working yet. These adaptations ensure it gets enough oxygen and nutrients. Think of it like having secret passages, like the foramen ovuli and ductus anterius, to efficiently deliver what the baby needs. Additionally, tiny blood vessels act like roads to make sure everything gets to where it should for the baby to grow healthy and strong. Development of blood vessels. So, first, development of blood vessels will start with the embryonic mesoderm. The embryonic mesoderm is a layer of cells in the early embryo. It serves as the foundation for development of various tissues, including the cardiovascular system. It then goes on to the blood islands. Blood islands are like clusters of cells derived from the embryonic mesoderm. These islands specialize in primitive blood cells, initiating the formation of the circulatory system. And then it ends with angiogenesis. Angiogenesis is the process of forming new blood vessels. Blood islands stimulate angiogenesis, promoting the growth of branching of vascular tubes. These tubes will eventually develop into the integrate network of blood vessels. On the right, I have a diagram of how this process works then. Fetal structures and connections. So we have the umbilical arteries, which carry deoxygenated blood from the fetus to the placenta for oxygen and nutrients. It bypasses the fetal lungs as they are non-functional in utero. Next is the umbilical vein, which transports oxygenated blood from the placenta to the fetus. It bypasses the fetal liver through ductus venous, allowing oxygen-rich blood to enter the inferior vena cava directly. Next is the ductus venous. It shunts oxygen-rich blood from the umbilical vein directly into the inferior vena cava, which bypasses the fetal liver, directing oxygenated blood towards the fetal heart. The ductus anterior connects the pulmonary artery to descending aorta, which bypasses the fetal lungs by allowing blood to flow from the pulmonary artery directly to the aorta, reducing the amount of blood sent to the non-functional lungs. And finally is the foramen ovule, opening between the right and left atria of the fetal heart. It bypasses the fetal lungs by allowing oxygenated blood from the right atrium to flow directly into the left atrium, avoiding the pulmonary circulation. On this slide, I have a representation of the flow of blood in the fetal heart. It goes from the right atrium down to the foramen ovule, over to the left atrium, down to the left ventricle, to the aorta, through the umbilical arteries, and then down through the umbilical veins, through the ductus venous, up from the inferior vena cava, into the right atrium, then into the right ventricle, and then the pulmonary artery and ductus anterior, and then the aorta again. Differences from an adult heart. In the fetal heart, blood is largely bypassing the non-functional lungs through structures like the foramen ovule and ductus anterior. The fetal circulation includes unique structures like the ductus venous, foramen ovule, and ductus anterior, which close or change function after birth. This blood flow in the fetal heart is optimal for the unique needs of a developing fetus in utero, adapting to the absence of pulmonary circulation. Oxygen-rich blood and oxygen-poor blood. Oxygen-rich blood composes of the umbilical vein, which carries oxygenated blood from the placenta to the venous, and the ductus venous, the foramen ovule, and the systemic arteries. Oxygen-poor blood consists of superior and inferior vena cava, umbilical arteries, and the pulmonary artery. Changes after postnatal and fetal heart. After a baby is born, the heart undergoes changes. The foramen ovule becomes the fossa ovalis, the ductus anterior turns into the ligamentum anteriosum, and the ductus venous collapses into the ligamentum venosum. These changes are part of the heart adapting to life outside the womb. The embryonic mesoderm, like a builder, first forms these structures and angiogenesis, like creating pathways, contributing to the blood vessel networks, laying the groundwork for a functional circulatory system. Here I have changes in umbilical vessels, umbilical arteries and veins. Changes. After birth, the umbilical arteries, previously carrying deoxygenated blood from the fetus to the placenta, gradually close and transform into the fibrous cords. The ductus venous. The ductus venous, which allows some blood to bypass the fetal liver, collapses and becomes the ligamentum venosum. Some importance about that, this closure redirects blood flow, adapting to the liver's postnatal role in processing nutrients. The ductus anterior, it transforms into the ductus anterior connecting the pulmonary artery and the aorta. Constriction becomes the ligamentum arteriosum. The purpose of this is closure redirects blood to the lungs now that the newborn breathes independently. The foramen ovule transforms into the fossa ovalis, and the function, it helps separate circulation between the left and right sides of the heart. Postnatal fate of structures. The ligamentum venosum. The ultimate fate, the ductus venous collapses and becomes the ligamentum venosum. And the function, the fibrous structure eventually has no active role in circulation, existing as a remnant of the fetal circulatory system. The ligamentum anteriosum, the ductus anterior constricts and becomes the ligamentum anteriosum. The function, like ligamentum venosum, this structure becomes a fibrous band with no active role in the postnatal circulation. And the fossa ovalis becomes the ultimate fate of this is the foramen ovale closes and becomes the fossa ovalis. The function, the fossa ovalis is a depression in the interstitial septum, serving as a remnant of the fetal structure, but no longer allowing blood passage. Some essential terms that was talked about in this presentation. In simpler terms, these words describe key elements in the journey for early embryo development to the unique features of the fetal circulation and the structural changes that occur after birth. Conclusion of fetal circulation. Understanding how a baby's heart works before birth is like knowing how special tunnels to get oxygen and nutrients without using its lungs. The blood vessels act like tiny roads to make sure everything goes where it needs to. After birth, these special tunnels close and the baby's heart starts working differently. Knowing all this is super important for making sure the baby stays healthy when it is born. Questions are welcome. Hope you enjoyed my presentation. Thanks.